I'm Petr Kadera. I'm with the Czech Technical University in Prague, and I will use this opportunity to introduce to you our approaches how to automate flexible production systems. So the motivation, as it used to be for the last 30 years, was that there are increasing demands from customers. Customers want to have higher frequency of new products. They want to have the tailored products. So there was an example with Adidas Speed Factory that was producing the shoes, pair of shoes, exactly according to the customized design of a specific customer. And there were many reasons published and communicated that it's necessary to increase the flexibility. Although we saw with Apple, for example, that maybe the mass production and the perfectly tuned products that didn't have that much flexibility as Android-based phones were still a perfect choice for many customers. But with new circumstances and the series of crises we live in, the pandemic situation with COVID and now the troubles with supply chains shows that the flexibility isn't like a nice have to have, but it's something we really must adopt to be able to survive the challenges that we have to face. So it's necessary to be flexible, to resist to interruptions in supply chain, to be able to change the production processes, to replace one material with another one. And this is something we are not ready with the traditional automation. As Napoleon said, the plans are useful, but the planning is everything. We really need to closely connect the ability to flexibly plan the production with the industrial resources. So I will start with a description why the current traditional systems are not enough. Then I will show how multi-agent systems can help us to make control more flexible, and then how model-driven development also provides specific capabilities that makes the system more adaptable. So this is the traditional automation pyramid we know from books for the last 30 years. So there's a shop floor at the bottom, there's a SCADA, MES system, and ERP system. The construction of the system starts at the bottom. You design the production line and you build another system on top of the previous. Of course, if you want to replace something at the shop floor, you need to rework all the consequent systems. And according to this analysis, 55% of the cost goes to the planning and engineering task. That's why, for example, in automotive, there is the re-engineering very rare process. So in automotive, one production line is designed and then is used for 7 years, and then with no reuse of the components, a new production line is used. So greenfield manufacturing instead of brownfield. So how multi-agent systems can change this? So at the beginning, what is an agent? Agent is an autonomous and cooperative unit. It can be logical, virtual software agent that, for example, provides some planning capabilities, do some computing stuff, or can be physical. In this terminology, it means that it's connected to a physical device, for example, agent representing a robot with certain capabilities. The agent is aware of its role in the world, so the agent knows what it can provide to its environment, what capabilities it can do. He knows what he wants to achieve, so what's the state he wants to achieve, and he keeps it in his own model. And it's proactive and cooperative to achieve the goals he has. And he does it with interaction with environment, interaction with other agents, or with the physical world by actuators or sensors that is sensing the world. The agents use communication based on messages. That's why they are a perfect fit to connect various systems, legacy systems with new systems based on different programming languages, because the communication is based on on messages. Gold standard for communication between agents is old known FIPA ACL language, which is a atomic communication element with defined structure that's actually based on a theory of communication X already defined in 60s, previous century. So, and it's actually shown as a very powerful way how to decompose conversations. The agents use protocols. They actually define the correct behavior. They define how you can react to some messages, and this is the thing that increases the interoperability between various agents. Now, this was the overall background in the agent world. But if you want to use agents to control the physical system, which has some real-time expectations, you need to combine this object-oriented approach capable of describing the agent behavior with the low-level control capabilities, which are typical for the PLCs. So there is a system called agent cooperation system that combines these two worlds. It has a shared memory and control interface that is able, without the real-time constraints, find new strategies, but then project the strategies into the real-time system to be executed in the same way. So such a system was used to automate a solution for control of chilled water system at a US battleship. So the task was to automate fully manual system where a commander actually gave some instructions to the sailors what valve should be open at particular state of the ship operation, and there was no way to automate it with one central system, because this central system would be a central point of failure, and if this part was damaged, then the whole system would be out of order. So instead of that, the agents were used not only to distribute the behavioral system, but also the physical component. So the system was controlled by 23 PLCs. Each PLC was hosting specific agent responsible for a part of the ship. And here we can see the model of the system, and each device, you can see here, when needed cold water, actually communicated with the agent that was able to provide the coolant, and also with the valves and pipes to find the optimal way for the current situation. So the part of the system was damaged, the system was able to react to that, and by the negotiation found the optimal situation for the state. And it was the biggest advantage of this approach, because it wasn't possible to predict in design time what are all possible situations, how the system can look like, and the system was able to find it based on the current situation. So this system brings the current, the runtime flexibility, but there are some drawbacks, of course. The first is that it needs some specialized development supportive tools to be able to design such a system. It also shows that the negotiation complexity is tremendous with this growth, the size of the system. You need to keep the actions quite simple, otherwise the response time of the system is quite long. So some of these troubles can be overcome with model-driven development. So it's based on nice sentence. Everything is a model, like everything is an object. In object-oriented programming, in model-driven environment, there is one through. Everything is a model. In model-driven development, there are meta-models that actually provide the conceptualization of a certain domain, and to define the vocabularies and rules that needs to be followed in all the models for the domain. Then there are transformations that transform one representation of the system from one model to another model. And we can use to implement this, for example, UML, typical tool for model-driven engineering, or ontologies, PDDL, or ER diagrams. So the model-driven development was used actually also for the multi-agent systems, because the agents provide the flexibility in the runtime, but in the design time, actually, to create a new version of a multi-agent system is quite demanding task, and model-driven approach actually can help you from the models of the agents instantiate a new model based on the configuration of the new system. What you can see here downstairs is an example of a model-driven control. We have a models of the conveyor system, where are the stations, the positioning stations where we can park the shuttles. We have the models of robots, what the robots can do, and what are the capabilities of the robot depicted in a model. And this model is done in the PDDL language, planning domain description language, that actually in the one part, which is called problem specification, defines the current state of the system, what are the current positions of the robots, of the shuttles, of the material, but also the general domain specification. For this example, I'm speaking about this domain about Lego. Lego, and it says that, for example, to place one Lego brick to somewhere, you need to have the connection pins underneath the brick. You can put it into the air. And this is the result. So you define the first model in Lego Digital Designer, a software tool you can download from Lego pages. You create the structure you actually want to build. And then the first transformer transforms this model from the Lego format into the PDDL. We have a static representation of the Lego domain, which says actually what are the possible actions and what are the effects of each action. And then we run a general purpose planning system that actually transforms or computes the plan that's actually transforms the system from the initial state to the goal state, to the expected state, which we select in the ERP system we have here. And we have the plan, which is then goes through another transformation, transformed from the PDL into the segments of actions defined in OPCA, and we instrument the robot to do it. So the great thing is that we maintain the model of the current state for the case that there's an error, there's some step can't be finished. So we have always the possibility to start the planning system again. For example, if there is a problem with one robot, we just change the problem description. We exclude the robot with a problem from the system, and we start again the planning, and we can recover automatically from the problematic state. The advantage here is that we can tackle with this approach more complex systems than with poor agents, where all the planning is distributed, but there is big overhead with the messaging stuff behind. So the optimized planning systems actually enable to compute more complex systems. It's also perfect that we can combine various industrial standards by the transformation, and we can use this innovative approach with standard equipment that's already adopted by the industry. Thank you.